Dominion modeling, measuring the speed of light. When you think of the fastest speed possible, you probably think of the speed of light. But can you imagine trying to measure the speed of light? Early Greek philosophers like Aristotle and early scientists like Kepler, Hooke, and Descartes believed that the speed of light was infinite. Others like Roger Bacon and Francis Bacon, no relation, thought it had a very large but finite value. Galileo did one of the first experiments to measure the speed of light. He had two observers positioned on hilltops, less than a mile apart, signal each other with lanterns. He didn't discover anything conclusive, though he suggested that the speed of light, if finite, was significantly greater than the speed of sound. In 1676, a Danish astronomer named Ole Rømer observed something strange about the way Jupiter's moon, Io, disappeared in its orbit behind the planet. When the Earth was nearest to Jupiter, the predicted time of disappearance was very close to the observed time. But when the Earth was on the far side of its orbit from Jupiter, the observed time was many minutes later. Rømer was the first person to recognize that the time differences were due to the delay caused by lights having to travel the extra distance to the Earth. 2A Dimensions of Physics 2.1 Introduction. 4 centuries before Christ, the Greeks reasoned from their presuppositions regarding the nature of the world to unravel its mysteries. Their common-sense solutions were accepted for nearly 2,000 years. But when scientists during the Renaissance stopped trusting traditional science and began testing their observations with new instruments and improved mathematical systems, they discovered that God's universe was far more orderly than they had thought, often in unexpected ways. The essence of physics is to measure the observable world and describe the principles that underlie everything in creation. Physical theoretical principles are usually expressed or defined by mathematical formulas. As instruments and measurements improve, scientists must constantly refine their theories to fit the data. To ensure that he has the best possible data, a physicist must know what to mean. Sure, how to measure it, how to record his measurements accurately, and how to use the measurements to produce mathematically meaningful results. 2.2 The SI. Early in history, each nation maintained its own system, the of currency, weights, and measures. With the rapid growth of science during the 18th and 19th centuries, nations recognized the need for worldwide standardized units. France took the standardization initiative in 1799 by establishing a decimal metric system consisting of the kilogram and the meter. The metric concept gradually gained wide acceptance among scientists. Throughout the 19th and 20th centuries, researchers sought to identify new standard units of measure and to more accurately define the existing ones. In 1960, the current metric system was renamed the Système International d'Unités, from which we get the abbreviation SI. It consists of 7 base or fundamental units and many other units derived from the base units. As new fields of science are established, new derived units continue to be added to the SI. 2.3 Meanings of dimension. The word dimension has 2 meanings, dimensionless, when used in physics. The first refers to the number of spatial coordinates required to describe an object. A point is dimensionless, a line occupies 1 dimension, and a plane exists in 2 dimensions. A volume of space, or a physical object, can exist only in 3 dimensions. The image on a TV screen is 2-dimensional, but a horse, Equus caballus, is 3-dimensional. The second meaning of dimension refers to a kind of measurable physical quantity. Examples include length, time, mass, resistivity, hardness, and momentum. Each dimension is described by a specific type of unit or combination of units. For example, length is measured only with units of length, meter, foot, etc., and density is limited to mass per unit volume, kgm cubed or 1 bm/ft cubed. 2.4 Fundamental dimensions. The universe consists of 3 principal dimensions: space, time, and matter. These are intricately bound together. One cannot exist alone without the others. In fact, everywhere we look, we see this kind of simultaneous unity and diversity. Many have wondered why the world is like this. Christians say that the answer lies in the triune God. He is one being existing in 3 persons. We see unity and diversity everywhere, because everything comes from a God who is one and three at the same time. Three at the same. 2.5 Space and length. Space is the apparently limitless three-dimensional volume within which all matter exists and all physical phenomena occur. Matter must exist and be present in order for us to perceive the size of space. If you looked into a space that contained no matter, you would see nothing. You would not know if you were looking into an atom-sized or a galaxy-sized space. The physical separation of entities in space, distance, or the size of an object, which itself occupies space, are measured in units of length. The metric unit of length, the meter, m, was originally defined as 1/10,000,000th, 10^7 power, of the distance between the Earth's north geographic pole and the equator, as measured along the meridian line of longitude passing through Paris. Because such a distance could not be reproduced in a laboratory, much less measured accurately, scientists fabricated a corrosion-proof platinum iridium bar, bearing two scribe marks 1 meter apart. This standard meter was retained in the International Bureau of Weights and Measures at Sèvres, France, under stringent environmental conditions that prevented expansion and contraction due to temperature changes. Even well-protected physical objects can be affected by environmental variables, so throughout the 20th century, scientists worked to abandon all references to dimensional standards based on man-made artifacts. At the same time, such objects became less useful as increased accuracy and precision were required. Scientists preferred instead to use extremely accurate and stable natural phenomena that could be measured in any properly equipped laboratory. In 1983, the meter was given its present definition in the SI as the distance traversed by light in a vacuum in exactly 129979245 second. 2.6 time. Have you ever tried to define the concept of time? Think about it. Everyone knows what time is, but try to define it. One attempt at an operational definition could be, time is a non-physical continuum that orders the sequence of events and phenomena. A continuum is any expansive entity without gaps or breaks. A moment of time exists in the indeterminable future, is experienced in the instantaneous present, and immediately moves into the past, where its significance can be understood only by one's reflecting upon past events. Notice the seamless, three-in-one character of time, again revealing the triune nature of its creator. Time is best defined by specifying the method of measurement that clearly differentiates it from all other physical phenomena. The SI unit of time is the second, s. The second was originally defined as 1/86,400 of a mean solar day, 24h x 60 mitmin h x 60s minobir 86,400s. Unfortunately, the rotational period of the Earth is not stable enough to define the second to the precision required for modern scientific purposes. In the mid-1950s, scientists invented very accurate timekeeping devices that used the resonant vibrations of a pure element to provide a time standard. A second is now defined as exactly 919-631-770 cycles of oscillating gaseous cesium-133 atoms. Atomic clocks are accurate to within 3 microseconds per year. 2.7 Matter and mass. As stated earlier, space would be dimensionless without the presence of matter. Matter can be operationally defined as that which occupies space and has mass. We know what space is, but what about mass? The mass of an object is a measure of its tendency to resist a change in motion. You will learn more about this attribute when you study Newton's laws of motion in Chapter 6. A normal object's mass is constant, regardless of its location in the universe, and that mass has gravitational attraction for all other matter in the universe. Large amounts of matter produce large gravitational forces. We will discuss gravity in detail in Chapter 7. When the metric system was established late in the 18th century, an attempt was made to define other physical properties that relate to the meter. For instance, volume could be defined by cubing a linear metric measurement. A unit of mass could then be defined as the mass of a specified metric volume. The mass of 1 cubic decimeter 1,000 cubic centimeters, or 1 liter, of pure water was first used to define the kilogram, kg. Scientists soon recognized that even the relatively large volume of 1 liter could not be measured directly with the desired precision. So scientists manufactured a IKG cylinder of PT alloy, called the standard kilogram, to replace the water standard. Its dimensions and the alloy mix of 90% platinum and 10% iridium are reproducible to a much higher level of precision than is possible with the water standard. The standard kilogram is also retained at the International Bureau of Weights and Measures. It is the only SI standard that is still based on a manufactured object. Even this may eventually change. Scientists are currently investigating various ways to redefine the kilogram. One method defines a kilogram as the mass that can be levitated in a precisely measured magnetic field of a specified strength. Another definition, which seems to have more promise for adoption, involves counting the number of atoms in a perfectly machined sphere of pure silicon-28, having a mass of 1 kilo. The spheres have been fabricated in Australia. When physicists finish counting, the number of atoms of silicon, not their mass, will define the kilogram. The 7 fundamental units of the SI are listed in Table 2.1. Note that there is a difference between the name of a physical dimension and its unit of measure. There's also a difference between the unit symbol and the mathematical symbol used to represent the dimensional quantity in physics formulas, the meter, second, and kilogram. And combinations of these units will be the only units of concern for the chapters dealing with motion and mechanics in Unit 2. The other SI units will be introduced later as needed. 2.8 SI Derived Units. Scientists deal with many more dimensional quantities than those listed in Table 2.1. For example, there is no fundamental unit for area. However, area can be represented by the square of length, which has the SI unit square meter. Similarly, speed is represented by the dimension of distance per unit time, with a unit of meter per second. Such dimensions and their associated units are derived from the SI fundamental units and are called SI derived units. Some derived units have been given special names and symbols. Examples include the SI unit for force, the Newton 1 Newton, Leverage 1 kgm square centimeter, and the SI unit for electrical charge, the Coulomb, 1 Coulomb, qua 1 AS. Some SI derived units are obtained from other derived units. For example, the SI unit for work and energy, the joule, is defined as 1 joule, 1 Newton meter. 2.9 unit conversions and analysis. Is the size of a virus more appropriately reported as 0.0000005 mm, or 500 nanometer? The basic SI units and their derived units often are not conveniently sized for use in every conceivable measurement. The founders of the metric system recognized that a method was needed to provide larger and smaller increments of the base units that would be convenient for any measurements that might be required. Prefixes were developed that, when combined with a given base unit, indicate the size of the new unit. Table 2.2 lists the named metric system prefixes, the prefix symbols, and the factors by which the base unit is multiplied. Note that, for consistency, the gram is the base unit of mass. However, the SI fundamental mass unit is the kilogram. The prefixes that we will use most frequently are kilo, centi, and milli. It is often necessary in science to perform calculations with similar dimensions that have different sized units or non-S1 units. All similar dimensions should be converted to the same units before you calculate. You accomplish unit conversion by multiplying the quantity by a conversion factor, a fraction that contains both the given and the desired units. In order to preserve the size of the original measurement, the conversion factor must be equivalent to 1. Its numerator and denominator must be equal-sized quantities. To find the correct ratio, we start with an equation relating the two units. For example, LMH 100 cmh. The factor required to convert from meters to centimeters is found by dividing both sides by 1 nam. Note that the unit we are converting to is on top. If we needed to convert from centimeters to meters, the conversion factor would be 1 meter 100 centimeters. Both ratios are equal to 1 because the numerator and denominator are equivalent. When several simultaneous unit conversions are required, such as when converting MIH to MS, we multiply the appropriate conversion factors together in any order, taking advantage of the commutative property of multiplication. We use a mathematical aid called the unit analysis bridge to help with conversion factor unit cancellation and to organize the solutions to physics problems. Look at Figure 211. The horizontal line corresponds to the fraction bar, representing the division operation, in any fractional numbers involved in a calculation. The vertical lines correspond to multiplication signs between factors in the calculation. Identical units that appear on opposite sides of the horizontal line may be canceled as usual. To see how this process works, study Example 2.2 below. After cancellation, the result is obtained by multiplying and dividing the remaining numbers in units. The key advantage of the bridge method is the convenient arrangement of factors, which eases the cancellation of like units. When solving physics problems using the bridge utility, we can often check the setup of the solution by analyzing the units that remain after cancellation to verify that the resulting dimensional units are the ones required for the solution. This process is called dimensional analysis, or more commonly, unit analysis. Valid physics equations must have the same dimensions on both sides of the equal sign. Dimensional inequality is a guarantee that the solution will be incorrect. Of course, the equation can have equivalent dimensions and still have an incorrect arithmetic solution. Dimensional analysis is only a check on the setup of the solution.